We're gonna learn about efficiency now.
Yay!
Part 2 of the last
Oh, let's be efficient.
episode. This is like the Lord of the Rings. It's the last movie, but it's part 1 of the last movie. Or Harry Potter. Does anybody know what this is? It's a light, but it's made of a bunch of little squares. Do you know what the little squares are? Small lights. Yeah, that's what they are. Dylan, you're right. Small lights. What kind of lights? LEDs. Good. Do you know what LED stands for?
Little electricity.
It stands for light emitting diodes. Actually, there's a really interesting story.
Is there?
Yeah, I didn't tell my other class about this. I forgot, but
Let's hear this.
oh, I don't have it. I lent it out. But there's a book called Brilliant, and it's about the story of this Japanese guy who made LEDs workable.
Wait, sorry.
Yeah.
Isn't that LED stand for little electricity?
LED stands for light emitting diode.
Why don't they make it back?
It would be good. Little energetic dinosaurs would be good. Yeah. This is a very efficient type of light. If you go on in physics, you'll learn a whole bunch about how those work. This is the kind of light bulb that I grew up with, and I have in my house. They're really actually pretty cool. There's a little thing that goes up and goes, and it goes down and it connects there. And you just run electricity through it, and it creates photons of light when it gets hot, basically. Those worked really well, but they're not particularly efficient. Yeah, they don't make that much light compared to heat. So they're inefficient. Did I show you the thing with the pencil lead?
Yes.
It glows? Okay, so that's basically what this is. By the way, do you want to know?
Tungsten.
Yes, the filament here is tungsten. That's the part that glows. The very first ones were bamboo, actually.
Let's do it.
Yeah, we should try it. Now, oh, I need my hat.
Try it by using someone's finger.
This is what physics teacher. Yeah. People just come in and get us candy. Thank you, Denise. You want to hear of the conspiracy theory?
Yes.
This is a real one. It's true.
It's true.
Okay. The world was dark, right? Evening comes, sun goes down. That's it. We just like sit around, go to bed. Can't read, can't do anything. We need light.
What about candles?
We have the movies.
Edison tells everybody that he's invented the light bulb. He did it. Someone else did it before, and he didn't even have it done then. He invited all these newspaper reporters to come see his new light bulb. But he said, it's secret technology. You can't spend a long time in here because I don't want you reporting my secrets. And only one person at a time. So he pulled back the curtain, and the newspaper reporter would go into the room, see, oh my gosh, it's so bright, it's so great. How long does it last? And he said, lasts forever. And then, but you can't stay because you're going to steal my secret, so go out. And then when the newspaper reporter went out, the person, his assistant from the back, came in and went, new light bulb. Because it really only lasted like 3 minutes. And then it blew up. But he told everybody that it lasted forever. And they believed him, and they wrote all these newspaper articles. And he got so much investment from that publicity that he was able to spend enough money hiring physicists like you to build enough light bulbs that eventually they figured it out. And so that's why we have these light bulbs. But then,
What a legend.
an interesting thing happened.
What?
There were 3 companies in the world that manufactured light bulbs. In North America it was Philips. Have you ever heard of Philips, that company?
Yeah.
They had a problem because their light bulbs were so good. People would buy the light bulb, and then they never needed another one. And this was a big problem, right? Everyone's got a light bulb and then they're done. So they actually met, these 3 companies, they had this meeting, There's all this documentation on it. They like wrote down it. And they said, okay, look, we're gonna sell all these light bulbs, and once everybody has one, we're finished. So, you guys, we gotta start making worse light bulbs.
What?
They actually gave themselves rules. They said, you cannot make a light bulb last longer than 1,000 hours. It's about 3 to 4 months. This is accurate because I was the one who replaced the light bulbs in my house, and I did it always like 3-4 months. Boom, be gone. You know, just put a new one. And that's true. There's a light bulb in a fire station in England. It's one of the original good light bulbs, and it's still on, and it's been on for over 90 years.
Whoa.
So that's a conspiracy theory. But it's
Dang,
real.
How does a mechanism work to keep it like that long?
Just a good filament, good thicker filament. There's also these ones. They tried to make these ones. They are efficient, but they're kind of toxic because they have a transformer at the bottom. Okay, what is efficiency? Efficiency is like, well, you tell me. What do you think efficiency is? Ty.
In terms of light bulbs, it would be the ability to produce light comparable to the energy you put in.
Oh, that's a great way to say it. Gordon.
How many percent of the energy transferred to the energy? How much?
Good. So the percentage of energy you get out compared to, as Ty says, what you put in. Good explanations. Jeffrey?
Yeah, like the amount of energy that you change to a desired energy type.
I'm glad you said that. The desired energy. Asal.
The wasted energy gets converted into heat.
Ah, okay. So that's another way to think of it. How much energy gets wasted, transformed into something we don't want? Who decides what kind of energy we want?
You.
Yeah, I suppose we do. If you have, if you're on a train that burns coal, and you're shoveling the coal into the train to move the train, what kind of energy do you want?
Heat. Steam.
Kinetic?
You're on a train. Do you want the train to be hot?
No.
What do you want the train to do? You want it to move. What form of energy is that? Kinetic. So you're looking for kinetic energy, right? The heat is kind of a byproduct. But if you're the guy shoveling the coal into the train and you're in the middle of winter in Siberia, a little bit of heat would be nice too, right? So it's up to us to decide what type of energy we're looking for. It's not, heat is not always bad, right?
Plus.
Thank you. When I was in high school, I helped install a furnace, natural gas furnace. And it was basically a blowtorch with some pipes attached to it, right? Pretty inefficient. We're talking like 50-60%. The natural gas furnace in my house, which I installed when my daughter was born, is close to 98% efficient. This is engineering. It's all coils and stuff. The heat gets burned, it goes into the house, and the heat that's going out the exhaust, there's coils that collect that heat and recirculate it back in. And you can keep a lot of that heat, so it's more efficient. Parsa. Maybe, but we've never found it. That's the best I can answer that, Jeffrey.
So.
I don't think we found it.
So let's say I make a heater. Like there is a coil. There's a
Sure.
coil. I blast electricity through it.
Okay, yeah.
Heats up.
It heats up, yeah.
It heats up.
Yeah.
And it gets, it glows as well.
Okay.
But I mark it, if I say the glow is so that people know it's working, so they don't burn themselves. Can I market it as a 100%
Well,
efficient
sure,
heater?
yeah. If you say we want these 3 forms of energy, then you could say it's 100% efficient.
So I can market it as a 100%
If you say, yeah, we
efficient.
want to like heat up the car and do all those things, then sure. Ty.
Free marketing.
watts.
Watts, yeah.
Isn't fusion energy near 100% or over 100%?
Well, so okay, I'm glad you brought that up. For you going on in physics, it's important to understand that the energy of the conservation of energy is always true in our universe. But what is also true, which might not be apparent to you right now, is that mass, like matter, and energy, actually the same thing. They're different forms of our universe. That becomes more apparent the further you go on in physics. Lisa Meitner, actually, right here. Denise is going to make this drawing for us. Can you see her? She figured out nuclear fission, which is the changing of matter into energy. So we can change energy into matter and matter into energy. So in a way, you're right, Ty. If you said, what's the efficiency of a fusion reactor? In other words, how much energy do we have to put in order to get this out? Well, it could be well over 100%. But if you're counting the energy that's already there in the matter, then it's not 100%. Does that make sense?
Yeah.
That's a great question. But most of you don't have to worry about that. Okay, machines are useful because they allow us to use less force over a longer distance. So we're talking levers, pulleys, ramps, things like that. We can do the same amount of work with less force. Whenever you use a machine to do work, some energy is always wasted. What does that really mean?
Efficiency is slow.
Is it gone?
No.
Transfer time.
It's transferred to another form on the machine.
Good. It's transferred into a form that we don't really need or want. Usually this is due to the generation of heat due to friction. There's a lot of friction losses. Yes? Yeah.
If you use less force
Yeah.
to go like the same amount of distance,
Yeah.
wouldn't you be
No, you use less force to go a longer distance.
Okay, but if you went the same distance and used less force, that would be like less work.
Yes.
Okay. But why, like, if you go the same distance and use
Yeah.
and go a different speed, I still don't understand why that's like the same amount of work, even if you get there faster.
So I have a kind of beam here, and I'm going to put a mass on the end of it. And I'm going to, if I lift this up, I have to use the force of gravity on this to lift it up, right? But if I have a long lever like this, I can push down a very small amount, and that mass will move up. So if that's 10 centimeters and this is 100 centimeters, I can lift it with 1/10 of the force of gravity. But which one moves more? My hand is moving a lot more than the mass, right?
Yeah.
This is called a lever. So if I want to lift something really heavy, that thing's not very heavy, but imagine there's something really heavy on the end. I can push down with a small amount of force and I can lift that thing, the heavy thing up. But I have to push for a longer distance. So the work stays the same. Force times distance is the same. You can play with, oh no, did it again. I always lift up the mass that I'm using to hold my HDMI in.
The pulley systems are the same.
Yeah, the pulleys are the same, and so are teeter-totters and incline planes, and that's probably about it. But. Can someone ask Mr. Rao to buy me a new HDMI? Now I can't see anything. I can't see my screen or the projector. Yeah, go ahead, Gordon. Okay.
That's good.
Yeah, so all these simple machines, it's all about the multiplication of force and distance. Sometimes you want the opposite, right? You want to go a shorter distance with more force. Like if you want to fling something, that didn't work very well. If you want to fling something fast, you can move a small amount of distance and get a lot of speed on the end, right? But it's always the same amount of work, and usually you get less energy out because there's some friction in the machine. The efficiency of a machine is work out, this is like desired work, divided by the work we put in. So Parsa asked, is this ever 100%? In the real world, no. Your percentage is always less than 100. If you calculate a percentage that's over 100, you did it wrong. You gotta flip it over, okay? So it's kind of easy.
What if we clear it?
If you don't know the actual work, like the defined amount of energy, but you know the power, you can also do the power you're getting out divided by the power you put in. And you're going to get a decimal and you multiply that by 100, and that's your percentage. Okay. Efficiency has no units, it's just a percentage of energy over energy. This makes sense? The formula is there. Work out over work in. And you decide which type of work is desired. Okay, try this.
What was the other one?
Power out over power in. Not working?
I printed it like 3 times darker, and so it worked.
You know what? I have a sheet of glass.
Let's trace it on the color. I'll come by and I'll get transparent paper. I went to the library.
It's funny, like we used to have so much stories. People threw it away and like. Just trace it. I'm sure. You can trace it on here.
When you pop those, there's way more cookies because they take away, so you can make it pop out.
A Sharpie?
Yeah. Can I cut your bag?
Yeah. I don't even know. Did you guys do this? Do you know what to do yet? What are we gaining? If you push the lever down, what kind of energy are we trying to get? Potential, gravitational potential, right? Can you calculate it? This is the mass of 50. How far up is it moving? It's 10 centimeters, so 0.1 meters, right? So your height of the object, as Dylan says, is 0.1 meter. Your mass is 50 kilograms. And so we can calculate the EP gained by using MGH, right? So what is that? 5 times, about 50? 49? We'll say 49 joules. So this is the work we get out.
Wait, what is work out again? Like, when you say
It's
work
like
out,
the desired work.
like how much you think you're gonna get?
Well, this is how much we actually get. This is desired. Or what's a better way to say that? Like wanted energy? Useful energy? How about useful energy?
So it's the work that you want to get out.
Correct.
And then
I mean,
what's work
heat is
in?
useful as well. It's just, do you want it or not?
So the work that you put in was the work we did to push this down. So we applied 75 newtons.
Okay.
And how far did we have to push? 1 newton, right? So our work in is our force applied times the distance, which is 75 newtons times 1, which is 75. And so our efficiency is work out over work in. So yeah, 66, 65 is it? 49 joules over 75 joules. So do you guys get where we got the 75? It's the force times the distance. Distance happens to be 1, so 75 times 1. And you should get about 65% out of that. So that means that this lever will give us 65% of the potential energy out of the work that we put in. What happens to the rest of it? We lose it as heat, like in the ramp and in the lever and the fulcrum and all that stuff. If you're an engineer, how can you increase efficiency?
Use friction.
Reduce friction. How do we reduce friction?
Yeah.
We fly to space. It'll be way more efficient.
Vacuum.
Sure, you could use vacuum or magnets. What's a simpler way to do it? But you could change this. What could you put here to make less friction? You could put lubrication. You could oil it. You could put a bearing there. You guys heard of ball bearings?
Like on the ball cap.
Yeah. So instead of rubbing on the thing, it's actually rolling little balls in there. So that's engineering. A lot of engineering is reducing friction. Up knees, I'll be right. Well, that's it.
Engineers versus physicists. Which one do you like?
Yes. It's 1:26. Oh, are you done at 1:30?
Yeah.
Oh, you guys have done very well. It's very hot and stuffy in here. I want to put on record that I've really, really enjoyed teaching you kids.
Really?
Yeah, really, you're awesome people. I hope you go on and do great things.
Dylan is, huh?
It's not like our coffee.
Yeah, but only to some of my classes, not all of them.
Do they have a personal project?
Yes,
You're free. What do we have next week?
We live in a free country.
This has,
Oh,
On the Friday?
oh yeah, thanks, Dylan. Yeah, what's on Friday?
the final exam.
Final exams.